So this is the structure we are looking at today. It was the written exam of the 14th of January, 2025, in my structural design course here at Politecnico di Milano. The structure basically consists of a trusswork. So before we solve it, we have to bear in mind certain aspects that are related to trussworks, and specifically the fact that trusswork consists of truss members. By truss members, I mean members which are subjected to axial force only. That is because if you look at them, they all fulfill what I call the 3 golden rules in order for a member to be subjected to axial force only. These golden rules are: the member is straight, the boundary restraints are hinges, and there are no loads applied on the member. The only loads applied are at the ends of the members. In this, we basically, when we study this type of structure with these hand calculations, we are neglecting the self-weight, which of course in reality is there, and it's a distributed load along the member. But for the purpose of hand calculations, we neglect it because, first of all, it's small compared to the loads this structure typically bear, and the results are not so much affected. Besides, if you are into a design task, so you don't know the dimensions of the member, you cannot evaluate the self-weight. You simply cannot calculate it. Usual WebEx room, the usual. So, let's look at what the tasks are. The first task is work out the reaction forces at points A, here, and it's specified that it's a hinge, and G, which is here, okay? And this restraint here is a roller by means of rigid body equilibrium equations. As a matter of fact, when you have such a structure, first requirement that should be fulfilled is rigid body equilibrium. So we have to work out a set of reaction forces which fulfills rigid body equilibrium. Besides, in such a structure which is statically determinate, because it has only 3 degrees of restraint, this set of reaction forces is unique, okay? This is not the case when you have statically indeterminate structures. You can find infinite sets of reaction forces. Also, in that case, there is only one which fulfills at the same time rigid body equilibrium and compliance, okay? So for the purpose of rigid body equilibrium, it doesn't matter that your structure consists of a trusswork. You can simplify it by representing it like this. So basically, I don't care what's here inside. I don't care whether the structure has depth. The only thing I have to bear in mind is that equilibrium should be satisfied. What are the reaction forces? Here we have 2, because it's a hinge, VA and HA. And here there is only one, which is VG. Okay? So a hinge prevents 2 displacements, horizontal and vertical displacements. As a consequence, we have 2 reaction forces. This prevents horizontal movement. This prevents vertical movement. A roller prevents only the vertical displacements. That is the vertical displacement. That is why we have only 1 reaction force. Then you have to place the loads. P divided by 2. P and P. These are the 3 forces. The dimensions are given here. Basically, our trusswork consists of square modules. where the length of each module or the dimension of each module is L. Now here the obvious choice is to write horizontal resultant of the forces and put it equal to 0. That is a good starting point. As a matter of fact, if you write Rx equal to 0, which means the summation of all forces in the horizontal direction is 0, you basically only have one horizontal force, which is HA, and that is why we directly get HA equal to 0. Then you could go like a caterpillar and write vertical equilibrium, but that is not the wisest choice. Why? Because in the vertical direction you have two unknown forces, which means you get an equation where you have two unknowns. So it is wiser to write a moment equilibrium, a rotation equilibrium, about 1 point. And I will choose A. So I will make sure that the rotation of the structure with respect to A is equal to 0. So I'm writing MA equal to 0. This basically cancels out VA because its line of action passes through point A, cancels out also HA, although we already know that HA is 0, and it cancels out the contribution of that load equal to P divided by 2 over there. Okay? What is left is P here, and VG, which is here. So, right to left, first contribution is VG times its lever arm, L, and L, which means the lever arm, so the distance of force G, of force at point G from A is 1, 2, 3, L. And by writing this contribution as positive, I'm implicitly assuming that my convention is a counterclockwise moment with respect to point A is positive. Doesn't matter, there is no absolute rule as regards convention, sign conventions. As a matter of fact, if it's conventions, it means it's a conventional choice. The important thing is to be consistent. So once we go with counterclockwise positive, we have to be consistent in working out all the other contributions, which means P downwards with a lever arm which is 2L has a clockwise contribution, which means minus P times 2L is the contribution of this force here. Okay? And same for that P over there, which means minus P times L is its contribution, and this is everything we have on our structure. So, without even touching my calculator, Vg times 3L minus P times 2L minus P times L, this basically transforms into minus P times 3L, which means in the end Vg is equal to P. Okay? Here's the result. I'm showing it for the people at home. Okay? Now for VA, you have two possibilities. You do the same exact thing, but writing a rotation equilibrium with respect to G, or you can now use the vertical equilibrium, because in this case, you only have one unknown, which is VA. So the obvious equation in this case is to put Ry equal to 0, which means the summation of all forces in the vertical direction. Again, be consistent with your sign conventions. I will start with VA, so I'm assuming that upwards is positive. VA minus P divided by 2, which is downwards, minus P downwards, minus P plus Vg, because it's upwards, equal to 0. Now we already know, you see it here, close to the equation that Vg is equal to P. Therefore, I can simply cancel out this Vg with this P, minus P plus P is 0, and this all reduces to Va equal to P divided by 2 plus P would be 3 divided by 2P with a minus. I bring it to the right side of the equation, and it becomes 3 divided by 2P. Okay? These are my three reaction forces in the specific case of the written exam of the 14th of January. For these simple three equations, you got 3 points out of the available points. One for each reaction force. Okay? Now, we have to go to the second task, which is determine the axial forces in all members by means of either the node or the section method, and clearly indicate the value and sign. And by sign I mean compression equal C, tension equal to T of the axial forces. I am free to choose my method. Since I have to work out all the axial forces, I will go with the node method, okay? Where do we start with the node method? Either G or A. As a matter of fact, for the purpose of the axial forces, I would like you to observe that you don't need all the reaction forces. What you need is simply that one end of the beam is known, okay? So, for example, once I work out Vg, I could stop working out the reaction forces and start with the axial forces. I would then get Va as a final result. But in that way, I would not be able to check it, to check whether it's right, okay? So I will go with the node method, and simply for the purpose of the usual conventions we have, I will start from A, okay? As a matter of fact, makes no difference. Again, you could start from G, you could start from A. A, since it has two members at right angles, is simpler to study. But again, doesn't make any difference. So what is the situation of node A? We have a reaction force, which is Va, and we now know it's P. Since we got, sorry, not P, of course, 3 divided by 2P. Since we assumed it to be upwards, and we got a positive value, it means the force is actually upwards. Then you have two straight members. One is horizontal, it's called AC, and one is vertical, and it's called AB. My way of doing things, but again, it's my way, it's my convention. I assume the axial forces to be positive if they are tension forces, which means tension forces pull on the nodes at which they act. This is called NAB. This is called NAC, and this is called NAB. What do you do with the node method? You write equilibrium equations for a single point in the plane of the blackboard. You only have two equations available: vertical, resultant force equal to 0, and horizontal, resultant force equal to 0. You cannot write in a rotation equilibrium on points, okay? So in our case, what are the two equations? Rx equals 0 immediately leads you to, there is only one horizontal force, NAC, which means it has to be equal to 0. NAC equals 0. Ry equals 0. We have Va and NAB both pointing upwards, which means Va plus NAB equals 0. This means NAB equal to minus VA, whose value is 3 divided by 2P, minus 3 divided by 2P. Look at the results. For the zero, we have no doubts about it. We don't have to specify whether it's tension or compression. It's simply unloaded. This is a negative result. I assumed it to be tension. Drawing it like this on the node means it's tension because it pulls. If I have a negative value, it means this is compression. Okay? This is the way to clearly indicate it. Okay? By writing this C here, I know that regardless of the sign here, you understand that it's compression. What do we have at the top node? We have, of course, NAB, but now NAB is known. It's 3 divided by 2P, and it's compression, which means it doesn't pull on its boundary joints. It pushes on its boundary joints, which means it goes like this, 3 divided by 2P. Basically, as you see, this member here transfers the reaction force to the top. Here you have a load applied, which is P divided by 2. Then we have this, which is, as you see, on top NBD. And then we have NBC. Now, before even starting with the calculations, it is obvious by looking at this node that NBD and NBC cannot be positive both, or they cannot be negative at the same time, because they both act this directly and this with its horizontal component in the same direction. So they should put themselves in equilibrium. So one should be tension, the other should be compression. Got it? What is the easiest equation to start off with? Well, in the vertical direction, we have two known forces, one which comes from AB and the load applied. And then we have the vertical component of NBC. So this would be NBCY. What equations can I write? NBCY, which acts downwards, plus P divided by 2, which is this load applied, minus 3 divided by 2P, equal 0. Thereby leading us to NBCY equal to P divided by 2 minus 3 divided by 2P is minus P. On the right side of the equation becomes P. And since this NBC is a force on a diagonal which is enclosed by a square module, we immediately know that the horizontal component would be the same. So in this case, the transformation for going to NBC is easy. You simply have to multiply by the square root of 2, meaning that NBC will be equal to the P times square root of 2. Much like in a square, where the side is 1, the diagonal is the square root of 2, which means 1.414. Okay? Larger. Then, what do we have? The horizontal equilibrium. In the horizontal equilibrium, we have MBD, and we have the horizontal component of MBC, which would be NBCX, which, again, being MBC a diagonal of a square module, MBCX will be equal to MBCY. Okay? So our horizontal equilibrium basically reduces to NBD, pointing to the right, plus MBCX equal 0, meaning that if this is P, this will be P, So it will, my equation will read MBD plus P equals 0, which means MBD equal to minus P. What about the signs? This is tension, this is compression. Okay? Now, how do we move in our structure? The wise choice is always to go from nodes with less members converging in them or looking at the unknowns. I started off from node A, where we had only 2 members, and this is why I could solve it immediately. Besides, as I pointed out, node A is also easier than node G. Then we had 2 choices. Here at B, we have 1, 2, 3 members. In C, we have 1, 2, 3, 4 members. So the obvious choice was to move to B. Now from B, we could go to C, again, 4 members, or D, 1, 2, 3, 4 members. It's the same. Simply, we have to remember that. In C, we have 4 members, 2 of which are already known, because we know the force in the diagonal and we know the force in the horizontal. At D, on the contrary, we only know this horizontal axial force here. So we move from A to B and now to C. Okay? And before doing that, I will start writing my results. So here I have 3 divided by 2P compression. Here, 2 architectural ticks, meaning that the actual force in this member is 0. Here it's P compression. And here I have P square root of 2 tension. Okay? If at the end of this part of structural analysis you draw a scheme like this with the forces indicated in this way, it's perfectly clear to me how your results are. There are no misunderstandings. Okay? So, to node C, we have the horizontal member to the left, which is unloaded. Then we have the diagonal member, which is subjected to a force, which is P square root of 2 tension, therefore it pulls. Then we have the vertical member, whose name is CD. Then we have another horizontal member, whose name is CE. And CE. Okay? Again, look before starting writing the equations. What is the most convenient choice in this case? Actually, in this case, there is no obvious choice. You can start with the horizontal equilibrium or with the vertical equilibrium, because these 2 forces are at right angles, so they don't interact with each other in the equations. Moreover, you have to remember that the components of the diagonal force are P and P. And thus, in a very simple way, what becomes the horizontal equilibrium? We have NCE pointing to the right minus P, which is pointing to the left. Is there anything else? No, because the force here is 0. So, equals 0, and NCE is equal to P. Sign, tension. Then we have NCD pointing upwards, plus P, because it also points upwards, equal 0, meaning we have NCD equal to minus P. And this is compression. Okay? Now we can move to node D, which is on top. What do we have at node D? We have a compression force coming from BD, whose value is P. We have a compression force coming from NCD, which is P. We have a load applied on top, which is P. We have a horizontal member, which is called NDF. So here we have NDF. And then we have a diagonal, whose name is DE. So this is NDE. Okay? Now, in this case, the choice of where to start from is obvious. In the horizontal direction, again, we have this axial force and the component of this axial force, so it's better to start with the vertical equilibrium. But the vertical equilibrium is very easy because what do we have in terms of applied loads on this node? We have P upwards and P downwards. Then we have the vertical component and the EY. But if these two forces cancel out, my equation simply reads NdEy plus P minus P equals 0, which means NdEi equals 0, which means NdE equals 0. Okay? If NdE is equal to 0, both NdEy and NEdX are equal to 0. So no contribution, which makes then the horizontal equilibrium, again, very simple, because it is simply NdF plus P equals 0, which means NdF is equal to minus P, which means it's a compression member. What?
And if the member equals to 0, what is considered? Compression or tension?
If you have the number 0, do you consider it to be positive or negative? Both or none of them. So we simply don't care, because we care about compression or tension since the design process involved is then different. But if a member is 0, we basically don't care about whether it's designed in one way or the other, okay? Anything will work well, okay? For you at home, the question was, is 0 force, compression or tension? Basically doesn't make any difference. If the force is 0, you don't have to specify whether it's compression or tension. It's simply not loaded, okay? So, time to update our diagram. P with a C for compression, 2 architectural ticks, P for compression in the vertical member, and then what do we have here at the bottom? NC was P in tension, okay? Now there are 3 members left, okay? So how will I proceed? Well, I'm at node D. If I move to node F, how many unknowns do I have? 2. If I move to node E, how many unknowns do I have? 2. So choice is indifferent. I will move to, again, A, B, C, D, E. I will move to E. and then to F, okay? Which means, at the end, when I'm here, I will have everything known, so the the calculation of node G will be simply a check of whether I did everything in the right way, okay? I will now have quickly to erase the blackboard. So as I mentioned, I am now at node E. At node E, we have a diagonal member which is unloaded, a horizontal member which is C, and we see there it's subjected to a tension force which is P, so I will put it directly here. Then we have a vertical member which is called NEF, EF, and therefore it has a force which is NEF. And then we have a horizontal force which is NEG. Okay? So again, the calculations are very simple in this case because as you see, there is no contribution from the diagonal member and therefore no contribution in the vertical direction other than NEF. So we'll cut the long story short. If you write the equation, this is equal to 0. And if you have this member to the left pulling to the left and this member pulling to the right, the obvious result is that they put themselves in equilibrium with each other. So this is equal to P, and it's a tension. Okay? And then we go to node F, which is at the top. We have a straight member, we have a vertical member, and we have a diagonal member. Okay? Now, from the straight member at the top, we have P compression. We have a load applied, which is P. Nothing from the vertical member we just calculated, EF, and the diagonal force, which I assume to be tension, and this is called NFG. Okay? Again, we mark the two components, NFGX and FGY. And also in this case, the equilibrium equations are very simple. And as a matter of fact, you see that we have only one unknown force with two equations available. So one will be used to determine the unknown. The other one will be a check if the results are correct. Okay? And carefully pay attention to how I use the symbols. Carefully pay attention. First equation, let me ask you, should we start with horizontal or vertical equilibrium? It's the same, exactly. So we'll start with horizontal equilibrium by simply writing that NFG X plus P equal 0, which means NFG X equal to minus P. Which means, between brackets, NFG Y equal to minus P, which means NFG equal to minus P square root of 2. But let's now look at the vertical equilibrium. And remember, everything is now known. We have no unknowns. So I will in this case write NFGY pointing downwards plus P. Is it equal question mark to 0? I cannot use this equation to determine NFGY because I already know it. It's minus P. And by replacing, here is minus P plus P equals 0. Yes, check. First proof that I probably did things in the correct way. Okay? And I'm putting myself in yourself when you're doing the exam. Of course, I'm doing things correctly. Okay? We are at the tutorial, so the minimum requirement is that I do the things right. Otherwise, what are tutorials there for? Now, final check is at node G. At node G, we have a straight member, horizontal, and the diagonal one, and we have the reaction force, which is P. What comes from the straight member? P tension. Like this. What comes from the diagonal member? P square root of 2, compression. So this is a compression force. Let me slightly transform this node to simply show you things in another way. Having this tension force applied here to the left, or having it here, always to the left, makes no difference. So we have P upwards, P to the left. What is the resultant force? P square root of 2 in the diagonal direction. And as you see, this node is in perfect equilibrium. So this means we did things in the right way. Okay? So to complete this part, I need to mark my results here. 2 architectural ticks here on this vertical member because it's not loaded. Then we have P here, tension, and we have P square root of 2 here, compression. As I pointed out also during classes, putting the arrows like this to indicate the sign is misleading, because thinking about the interaction between joints and members, I don't understand from this whether the arrows are pointing towards the joints or towards the member. Okay? Just to give you an idea also on the time, it took me 40 minutes to solve this part. Of course, I'm faster than you probably are, but I also took some time to explain all the different things I did. So this gives you an idea of how much time you need to solve this part. Now, second part of the problem, design and checking part. And for this, you have to take advantage of the design data and the geometric properties of the profile, which were given at the back of the page, okay? So the first question was, check the section of BC, assuming it consists of a hollow square profile with A equal to 40 millimeter and S equal to 30 millimeters. To solve this, we first of all need to move from symbols to numbers. So in this case, it was specified that the 3 main properties were L equal to 2 meters, P equal to 50 kilonewtons, FYD equal to 175 megapascals. Basically, the dimension of the module, the load applied, and the design yield strength of the steel. So we have to design member BC, and although I did things in a correct way and all the checks I performed confirmed my results, I still may have some doubts about whether I got things right or wrong. So I may want to check my results. How can I do that? Well, I can do a quick check with the section method to understand whether my design force in BC, which is P square root of 2, is correct. How do I do that? Let me underline it. You're not obliged to redo the calculations, only if you are not sure about your results, okay? And I am showing it to you just to show you another way of getting the things. So the check would be with the section method, and by checking it, and for checking it, I do this. I do a section cut, which is like this. Remember, the section method, in order for it to work, goes through section cuts which have, in the maximum case, 3 members intersected. Otherwise, there are too many unknowns. So I have my reaction force here, which is VA, and we know it's 3 divided 2P. We have P divided by 2 here, which is the load applied. We have a force here, we have a force here. What we are interested in is NBC, okay? What is the equation that I can use to work out NBC? This force is horizontal, this force is horizontal. This NBC has a vertical and a horizontal component, so I will write the vertical equilibrium. Ry equals 0, which means NBCY pointing downwards plus P divided by 2 minus 3 divided by 2P equal 0, meaning NBCY is equal to this reduces to minus P. On the right-hand side, it becomes plus P, which means NBC is equal to P square root of 2 tension as we previously worked out. So I'm quite confident with my results, and I will go with this force. Now, what is MBC in numbers? It's P square root of 2. I take now the calculator, as you all can do. So calculation is simple, 50 times square root of 2. The result is 70.71 kilonewtons. Okay? This is my design force. As it was specified at the bottom of the assignment, no coefficients should be added to the loads applied and the yield strength FYD as given above. So I will design for this force here. Okay? It's a tension member. How do I design tension members? You have to remember the theory. In tension members, there are no second order effects, which means tension members are not prone to buckling. The only thing you have to make sure is that the cross-sectional area is enough to withstand the applied force, which means assuming the cross-sectional area can develop its full plastic strength, the resisting force we work out has to be larger than the applied force. In this case, it was a check problem, so it was specified that the member BC consists of a hollow square profile with A equal to 40 millimeters and S equal to 3 millimeters, which means I turn around the page and I look for the profile, which is 40 times 3, so you can read its properties. A equal to 40 millimeters, S equal to 3 millimeters, which means profile is basically like this. It's a square hollow profile with a thickness of 3 millimeters and a dimension which is 40 millimeters, okay? The property we are interested in is the area. You can read it to the right in square centimeters. The area is 4.44 square centimeters. What is the resisting axial force of a member whose section is this and works in tension? The resisting axial force, plastic axial force, call it whatever you want, doesn't matter, is FYD times A. Each fiber is stressed to its largest value, which in our case is the yield strength. So the calculation, what does it yield? 175, it's megapascals. To be able to use the units of measure in the correct way, you have to remember that megapascals are newtons over square millimeters. Which means it's convenient to transform the area from square centimeters to square millimeters. How do I do that? You have 10 millimeters in 1 centimeter, which means you have 100 square millimeters into 1 square centimeters. So I basically have to multiply this number by 100. And I will divide it. Of course, the result gives you Newton over square millimeters times square millimeters gives you newtons. But I have this in kilonewtons, so I want the result in kilonewtons, which means I'm going to divide by 1,000, and I do the calculation. $77.7. What is the check? This, which is the resisting axial force, which is the maximum force the member can sustain, is larger than the applied axial force, which means my section is okay. So the answer to point C would be the section is okay. The profile chosen is okay. Second task is to design tension member. The member to be designed is CE. Where is CE? It's here. It's subjected to P and it's tension. Again, I would like to check my results before going with the calculations. So section method. This is 3 divided by 2p, we know it. Here there is p divided by 2. Here there is p. This is NCE. Then we have a force in the diagonal member and the force in the straight member. How do we check that NCE is correct? What equation do we write? If we have these two forces, we want to get rid of them, so we write a moment equilibrium with respect to the point of intersection of these two forces, which means we write a rotation equilibrium with respect to this point here, okay? Which would be point C, no, D. This is D. So MD equal to 0. What do we have? NC, which rotates counterclockwise, times the lever arm, which is L. Then we have 3 divided by 2, which rotates clockwise. times L, which is its lever arm with respect to this point here. Do not take it in the wrong way. It's not the distance between the 2 points, it's the distance between this line and this point here. So in normal direction to the force, to the line of action of the force. Then we have P divided by 2, which rotates like NCE. Lever arm is again L, equal 0. The result is minus 3 divided by 2 plus P divided by 2. So the result is, and L cancels out, of course, everywhere. The result is NC equal to P tension. So my result is correct. What is the force applied in NCE? So if it's P, it's simply 50 kilonewtons. What is my design equation? Basically, let's quickly go back. If the resisting axial force is Fyd times A, I have to determine the minimum area by making sure that at least this number here is equal to the applied axial force. Which means the minimum area is equal to what? To NCE divided by Fyd. This is my design equation. So with the right units of measure, 50 kilonewtons are 50,000. I can write it 50 times 10 to the power of 3 in scientific notation, divided by 175, and I will get an area which is in square millimeters. And in order to have it in square centimeters, which is what I have in my table, I will put 10 to the power of 2 here. Okay? So I can cancel out this 3 with this 2. And my calculation, therefore, is 50 times 10 divided by 175. Result is 2.86. This is the minimum area I have to provide. Let's quickly look at what the assignment specified. Design the section of CE, remembering that the most effective solution is the one characterized by minimum weight. Why did they put this? Because if you turn around the page and you read in the column area, the first section which fulfills my requirement on minimum area is section with A equal to 30 times 3 for the thickness, whose area is 3 divided by 24. But if I move further down, there is a section which is 40 times 2 with 304. Now this is a section which, even though deeper and wider, is preferable if the criterion is the minimum weight, because it weighs less. As you can see, 30 times 3 is 2.54. 40 times 2 is 2.39. Okay? Why do we choose the criterion of minimum weight? Exactly. It's like when you go to the butcher, okay, and you buy your meat or whatever on the basis of the weight, still is the same. So do not make this mistake. It's not the first one in line. It's the most effective. As a matter of fact, as you see, you have multiple choices. If you have multiple choices, what is your criterion? The minimum weight. So, on the basis of the minimum weight, the solution in this case was A equal to 40 millimeters, S equal to 2 millimeters, with an area which we call area provided equal to 3.04 square centimeters. Okay? If you look at the table, you realize that of the profiles provided, this was the area which was closest to this value. The design task ends here. You don't have to do a check to control whether this area is correct. If this is larger than this, the check will be automatically satisfied. Now, point E was check the section of FG, assuming it consists of a hollow square profile with A equal to 60 millimeter and S equal to 40 millimeters. Now, in the case of FG, which is here, you cannot do a check with the section method. Can you have a section which intersects 3 members and not more in your structure? Can you think about one? Whatever section you think about, you will reduce your problem to the node method. So one way to check it is instead of if you remember, we worked out NGF or NFG from node F. One thing you could do is work it out by starting from node G, okay? So we'll not repeat it because it's no different from what I did previously. So I will instead focus on NFG, whose value is P square root of 2 compression. Again, the value is 70.71 kilonewtons. We already calculated it for the first checking assignment, which was BC, again a diagonal member. So we are supposed to design a diagonal in tension, or to check a diagonal in tension and to check a diagonal in compression. Now, assuming it consists of a hollow square profile with A equal to 60 millimeter and S equal to 40. So A equal to 60 millimeters and S equal to 4 millimeters. What properties do we have in the table? We have, as you see, it's the last profile in the table. We have the weight, but we don't care about it because we are not supposed to use it as a criterion. The section is a given. We have an area which is 8.96 square centimeters. And we have radii of gyration, which are the same in the x and in the y direction, which are Ix equal to Iy equal to 2.29 centimeters. Now the member is in compression, and as we stressed a lot during the classes, compression means second order effects, which means prone to buckling. So this should be a big warning, and I will write it here with an exclamation mark or 2 exclamation marks, which means pay attention to what you do. But in case of checking, it's quite easy to perform the task because everything is given. So the first thing you have to calculate is slenderness, which means how elongated my member is with respect to its cross-sectional area. The indicator of this is a non-dimensional quantity which we call slenderness. The symbol used is traditionally the Greek letter for L, lambda, and it's calculated by dividing the buckling length, indicated by L0, divided by the radius of gyration. Which one would you take in generic cases? The minimum one. In our case, they are the same. Ix is equal to Iy, so we have no doubts about what to take. Okay. Problem is the buckling length. What is the buckling length in the case of member FG? In the case of member FG, which is in compression, and this is common to trusswork structures, the buckling length coincides with the geometric length. So we basically are thinking about buckling which takes place in this way. My member fails sideways by buckling either in this direction or in the other direction. Important thing is the points of contraflexion are located at the boundary hinges. And how much is the length in this case? Now, strangely enough, many people during the written exam use L instead of what? L square root of 2. In our case, so we have 2, which was L multiplied by the square root of 2 divided by 229. Careful with the units of measure. This is in centimeters. So it's wiser to have the length in centimeters. So it's not 2, it's 200 times the square root of 2 divided by 229. 200 times square root of 2 divided by 229. Result is 123.5, which I will round up to 124, because in the case of slenderness, rounding up is on the safe side. The higher the slenderness, the more prone the member is to buckling. From the table you had at the back of the page, you can work out omega as a function of lambda. Omega is an amplification coefficient we use to take the buckling phenomenon into account in a simplified way. So you move down in the first column, lambda 0, 10, 20, 120, and then you start moving to the right. 0, 1, 2, 3, 4, and 5, 220. Do you get it? Table is like this. First column is lambda, 0, 10, 20, you move down to 120, and then you start moving to the right. The first is 0, 1, 2, 3, until 5. This is how you get to the omega corresponding to lambda equal to 125. 0, 1, 2, 3, 4, 5. The omega you get for a slenderness of 120, oh sorry, I said 124, and I said then 125, so it's not 220, it's first one 206, 209, 212, 214, 217. Can you locate the number in the table? 217. 2.17. Third step is simply what? The equation you had at the bottom of the page. Can you see it? In the case of the compression member, the resisting axial force is the same as in the case of tension, Fyd times A, but then I divide it by omega. Since omega is a number which is always larger than 1, or in certain cases of slenderness equal to 1, this will be smaller than the corresponding force for tension. So what do I have? 175 multiplied by A, the area provided, which is 896, and I will put it in square millimeters. 896 divided by omega, which is 217. And then I will put divided by 1000 in order to get the result in kilonewtons. Calculation, 175 times 896 divided by 2.17 divided by 1000. 72.26. Check, because this number is larger than this one. The section is okay. Last point of the exam was design the section of DF. Where is DF? It's here at the top, and it's again compression, the value is P. So we have to design for a compression force equal to P, which means equal to 50 kilonewtons. Buckling length, in this case, as we previously explained, is L0 equal to 2 meters, which means 200 centimeters. No difference with the previous member. What is the problem in a design of a compression member? If we think about the equation, which gives you nRd equal to Fyd times A divided by omega, and we use it as we used the same equation or the corresponding equation in the case of tension members in the opposite sense, we have A minimum equal to what? N applied, which is NDF, times omega divided by Fyd. Okay? But we cannot use this one. Why? Because we know NDF, we know Fyd, we don't know omega. So this omega is a function of lambda, which is a function of the profile we choose, because it depends on the radius of gyration. So a direct way to immediately get a solution is not possible, which means you have to design by trial and error. But if you look at the table, there is something which makes it simple or simpler to do the design. Let's look how. So this can't be used, or let me say, can't be used directly to immediately get the solution. We have to make some tricks. So look at the table, okay? And look at the profiles with A equal to 40. How many we have there? We have 3 of them, thickness 2, 3, and 4. Among this group, what is the minimum radius of gyration? First one is 155, 152, 148. So let's think about this group of profiles as all having I equal to 1.48 centimeters. Okay? Let's group them and use as a radius of gyration for this group of profiles the minimum you have, which is the one corresponding to a thickness of 4 millimeters. In this case, what is the lambda? It's 200 divided by 148, which means 135. Which means omega will be what? Again, in the table, 130, 0, 1, 2, 3, 4, 5. 2, 4, 9, okay? Which means I can do the calculation with this equation for this group of profiles by using an omega 249. Do we agree that if I take here the minimum, it will be valid also for profiles which have a larger radius of gyration? Obviously, it's on the safe side. So the area minimum, assuming A equal to 40 millimeters, this is a strong assumption, will be equal to what? And the F, which is 50 kilonewtons, or in newtons 50,000, times my omega, which is 249, divided by 175, and I multiplied by 100 in order to have square centimeters. So I cancel out 2 zeros here and 2 zeros here, and I do my calculation. 500 times 2.49 divided by 175. Result is 7.11 square centimeters. How do I have to interpret this result? I interpret it in this way. If I assume that my section is one of the three with A equal to 40, I need an area which is at least 7.11. Do we have a profile with 40 millimeters of width and depth with an area which is at least equal to this? So, no solution available in this set of sections. So we now move to the next one. How? The next group is A equal to 50. What is, among this group of profiles, the minimum radius of gyration? 1.89, which means the slenderness is lambda equal to 200 divided by 1.89, which is 106, which means omega is, you tell me while I check it, for lambda equal to 106. How much? $1.73. Yes. Same calculation. A minimum, under the assumption that A is equal to 50 millimeters, will be what? 50,000 times 173 divided by 175 times 100 to get square centimeters. Minimum area is 494 square centimeter. Do we have one which fulfills this requirement? As a matter of fact, we don't have one. We have two of them, correct? So both solutions are possible, 50 times 3 or 50 times 4. Okay? Put red circles around these two solutions because they are both available. So both 50 times 3 and 50 times 4 are okay. Which one would you choose between the two? Less weight. Do we stop here? Do we stop here? We do not stop here. Why? Because we cannot rule out the possibility of having a profile with A equal to 60, which is the last group, which fulfills the check with a lower weight. As a matter of fact, look at the first one, 60 times 2. It has an area which is 464, okay? Close to this. and the weight which is less. One could say, yeah, but the area is smaller. Yes, of course, but I worked out this area with a slenderness which is 106. In the case of group with A equal to 60, the slenderness will be definitely lower. Let's check it. So we now go with an A equal to 60 millimeter. What is the minimum radius of gyration in this group of members? 2.29, okay? What is the lambda? Again, 200 divided by 229, which leads you to what? $87, which means omega is, again, 1.40. The minimum area in this group of sections is 50,000 times 140 divided by 175 times 100 for having square centimeters. Calculation. Guess what? 4 square centimeters. What profiles do fulfill this requirement in the group with A equal to 60? All of them. Which means I have 60 times 2, 60 times 3, and 60 times 4. So 2 in the group with A equal to 50, 3 in the group of A equal to 60. Circle them on your sheet of paper and now tell me, which profile do we choose? The first one or something else? First one, what does it mean? Now, in all the groups, we have 50 times 3, 50 times 4, 60 times 2, 60 times 3, and 60 times 4. Which one do we choose among these 1, 2, 3, 4, 5 sections? 60 times 2 is again the solution which makes sure that you have the profile with less weight. So it's the optimum choice from the point of view of the cost. Remember this, in design we typically have a variety of solutions. If we don't have any other requirements specified, we go for the minimum cost. And it's not a way of endangering the things, because we are sure that if we do our calculations properly, all the solutions fulfill the safety requirements. I think that from what we did, you could grasp the problem with the design of compression members. When we have to specify omega, we have to make an assumption. In this case of the square hollow sections, working group-wise on the basis of width and depth, so the first number in the table is an effective way to go. Okay?